Hello, so welcome to this lecture video. So this is about sample problem from 131 to 140. So this problem is okay. So we want to calculate the expected number of this, giving that like we want to find expected number of claim in May, giving that in April the number is 2. So the first we want to know what variable is about May, what is variable is about April. So here say N1, N2 for April and May, right? So this means we need to find this. We want to find expected value of N2 May when N1 equal to. We need to find this. Okay, so in order to find this expected value for this variable, we need to know the distribution for N2 under this condition. Or we want to find the density function. Okay, so we say we can find this when N2, so we just let the N2 can change N1 fixed. So N2 equal, let's say N2 under this condition, so we just can plug in here. So N1 is 2, so this is equal just okay. So N1 is we just let this as all a constant, like 3/4 or 1/4 2. 2 minus 1 become 1, so -2, and this is just 1 minus -2 into minus 1. Right? Or we just say this so this is not density function because the total maybe is not equal 1, but we just like this is, so we use a constant to modify. So we just put this as just some constant, then multiply 1 minus -2. Okay, so N2 minus 1, or just like K, we just say okay, Q says N minus 1. Okay, just like that. So we know this distribution is geometry distribution, right? So for this geometry distribution, so this should be just like that, equal P Q N minus 1. Okay, so what is a Q? A Q is just the 1 minus -2. Okay. Okay, so now the problem becomes easy. We say so for geometry distribution, this expectation is 1 over P, right? 1 over P. So what is P? So P, let's say Q equals this. So P, I'm sorry, P equal is -2. Okay, so equal is 2. So for this problem, what we want to find we want to find the, let's say we want to find this expected payment. So this payment, expected payment is, let's say, a man purchased a life insurance policy on his 40th birthday. So the policy will pay us if we die before that. So here, let's say, this is 40, and then this is 50, and this is 0. Okay. So if this guy died between 40 to 50, then pay so much, right? And if this thing like that happen here, die happen here, they pay 0. Okay. So this is the payment. So we want to find expected payment. So expected payment equal, so equal just this payment pay. So equal can pay this or 0, right? So we just need to find the probability for this thing happen. So probability is, so this is just this probability is probability for this guy's life will less than 50, but under those conditions t already larger than 40. Okay, so here we don't care. So this expected value is just equal 5, so is just equal this, right? 5,000 multiply this probability. Okay, t less than 50 under the condition t larger than 40, right? So here we just need to find this probability. So this probability equal, let's say for this one, so this one, put this. So this is just equal p t larger than 40, and then p t between 50 and 40, right? Okay, so to find those probabilities, so we just check the way the so here this is cumulative distribution function. So this is just the probability for t less than this t, right? Okay, so we can say that this is like for p t larger than 40. So we can, so what is larger than 40? Larger than 40 just equals this. Yeah. So so here's less than 40. So larger than 40 just this exp. So let's say the exp. Okay. So just 1 minus 1.140 over 1,000, right? So between 40 and 50 is just the this, right? So this is like xp 40 between 40, so minus xp 50, 1.150. Okay. So you should calculate. We can find this number, then multiply multiply 5,000. Okay. So for this problem, we want to find the probability. Calculate the probability that the probability for next matrix is king or queen size. So we want to find this probability. King or queen. Okay. So now let's say so here we have like 3 kinds of matrices: king, queen, and twin. So they have some probability, like some people will buy this, buy that. So we use this. Okay. So we use this graph. Can be king, can be queen, can be twin. Okay, so the probability, so suppose this x can be those things, and the probability for by king, so we just put this by kings, probability k, by queen size q, by twin is t. So we just check their relationship. So this is 1/4. So here, just changing those as mass. The 1/4 as many queen size as sold as king and twin combined. So we just convert this sentence into a mass equation. So from here we get this queen equal 1/4 of k king plus t. Okay, right? And so three times many king are sold as twin. So this is king equal 3 times many kings are sold. So okay, so this king equals 3t. Yeah. Okay, so then one more equation is that together add them up, k plus q plus t equal 1. So we can find this. So king or q is just equal k plus q, right? So we can find this. Okay, so for this problem, we want to find or calculate this variance for n. So what is n? N is number of injury. This n is person distributed with mean lambda. Okay, so this n is from person with mean lambda. So it seems like if lambda is fixed, then we know for person distribution, variance and mean the same, right? But here, this lambda is also can change. this parameter lambda is is uniformly distributed. So such a problem is, we say, changing parameter problem. So the parameter is not fixed. Okay. So here we have the formula. We say, suppose like we have the formula. We want to find variance for x. So this x is also related to other things, a landing variable, other landing. So we have this formula. We just remember this formula. So equal so v x when y fixed for giving y. So y is parameter. We can see equals as the plus v okay so x giving y fixed. Okay, so this formula we should remember. So vx equal, we just simply say that equal ev plus ve. Okay, so now we can apply the formula. Okay, so Vn, we put it together. Vn equal Vn when lambda fixed. Okay, so then the lambda is just y. The lambda can change. Yeah, so plus v e. Okay, there's n giving this lambda. Okay. Okay, so let's say, so when lambda fixed, so what is v? What is v n when lambda fixed? So we know this is just equal variance of person is just equal lambda, right? So just equal this is just equal e lambda, and so e n. So there's n person distribution. So this mean is lambda. So we say this is just equal lambda, right? Okay, so we have this. Okay. Okay, so then we find those e lambda and v lambda. So this this lambda follow uniform distribution between 0 to 3. So we say mean is 1.5. And variance, we have this formula, right? So equal variance is b minus a. This equal 3 minus 0 square over 12. So this thing you also should remember for uniform distribution. Let's say uniform distribution between a to b. This variance equal b minus a square over 12. Okay, so this equal 1.5 plus 9 over 12. Yeah. Okay. So for this problem, we will clear. We want to find conditional expectation, right? When y equal 2, we find this expected value for x. So we wanted to know what is the distribution for this x under this condition, or conditional distribution. Okay. So for this problem, let's say, so what is x, what is y? So here x is number of rows needed to obtain a 5. And what is y? Y is the number of rows needed to obtain a 6. So let's say, so the distribution for x giving y equal 2. So what does this means? This means y equal 2 means we need, so we already know like, so we roll this dice, so means like this is 6, second one is 6, this is not 6, right? Not 6. So this is y equal 2. So we just, so under this condition, we want to find the expected value for x. So at first, so this x is we like how many rows we need to get 5. So we just count. We will try again and again until we get 5. So such x follow geometry distribution, right? Just keep doing until you get a 6. But we have this condition. Okay. So this one we put this. Suppose this is we put this variable as z. So this z we can get this z can be first one get 5, right? So can be first row get 5. So second one cannot be equal to 2 because 2 second row is already 6. So this one can be 1 or 3. Or this like this time, so you get 5 here or get 5 here. You get 5 here, right? Like this. Okay. So we just put this into 2 parts. So let's say, so z equal 1 or not equal 1, or just start from here. We can say like, this one get 5, second one get 5, so we can forget this condition, like, so first one get 5, second one get 5. So this part, this expected value is 1 over p. So this expected value is 6, right? So we know this is like so how many times you can get 5? So we say probability to get 5 is 1 over 6, right? So this is should be like this is just the 6, but we count from here 1, 2, 3, 4. So this we say this average, this expected value should be 8. So 6 plus 2. So for geometry distribution, we have this, right? This number should be equal 1 over p. So here equals 6. Okay, so we say that this expectation equal. So this answer is x. So x when y equal 2. We put this into 2 parts. This one can be 1. So this one multiply the probability to say equal 1. So this conditional probability. So this one cannot be equal 6. First one cannot be 6. So we have only can be like 1, 2, 3, 4, 5. We have 5 cases. So get the 5 is 1 over 5, right? Okay. So then if z not equal 1, then we need to check this case like 3, 4, 5. So this equal probability is 4/5. And this mean or average become 8. Right? So this is the answer. Okay. So by some calculation, I think this equal 6.6. So for this problem, we have a moment generating function for x and y. So at first, we know this moment generating function for x plus y equal moment generating function for x multiply moment generating function for y. Okay? And this x and y are identically distributed, also independent. So this means this equal, we say equal mxt squared. So we have this, we say it's a square mxt squared equals this, equals 0.009 is negative 2t plus this. So we say this. Okay, so what is the mxt? So mxt is just so this one should be equal something square, right? So we find this mxt is like this is negative t, and this one, last one is 0.3 et. Then plus constant is 0.4. So we find this. Okay. So how can we get this? We just say, this is this thing square, this is this thing square, then plus constant. So we just square this and compare those, then we can find the constant. Okay, so this means this x, this distribution for x, actually can take -1, right? So then probability is 0.3, and x can take 1, probability 0.3, and take x equals 0, the probability is 0.4. Because this mxt, we say mxt moment generating function is just equal as tx, right? So this x can be only -1, +1, and 0. Okay. Okay. So now we know the distribution for x, then we can find what is the probability x less than or equal 0. So we find this probability less than or equal 0, x less than or equal 0. So less than, so this equal 0.3 plus 0.4. Okay, so for this problem 138, a machine consider two components life have the joint density function like this. Okay, so the machine operates until both components fail. So we let t be the time for the machine can operate. So this t equal so only when both components fail. So this is, let's say, like a v. So last one failed, then the machine stopped. So this is t equal maximum of x and y, right? So x and y are x the first component, lifetime for first component, y is last component, right? So we understand. So we need to find the expected value for t, right? We need to find this. So then what is the distribution for xy? So we say xy is the between this range, like x plus y less things. So this x plus y equal 10. Okay, so we know the range for xy is this triangle, and the density function is 1/50. So we can say this is uniform distribution in 2 dimensions. So the density function is constant. So this is t. So we can so t is maximum. So let's say where, okay, so we want to indicate maximum. So we just so in this line y equal x is here equal y and x is equal. So then in this part maximum x, right? So t equal x. So here t equal, here this part is x, and this part maximum is y. Okay. Okay. So we want to find et. So et. So we can. So et. We put this as d1, d2. So suppose this is d1. This is d2. So this is equal like, okay, d1 integration, then t equal x. So x f x y dx dy, right? So plus okay, d2. So for d2, this t equal y. So y f x y dx dy. So for this integration, this fx is constant. So this integration is easy, and also we find there's 2 parts symmetric, so same. So we just so this equal. So we put it to here. Okay. So equal 2 of this, right? So let's check d1, and this is just x, and density function 1/50. We put 1/50 outside. So dx dy. Okay. So for this integration, so determine x first or y first. So determine x first, we need 2 parts. So it's going to be better to determine y first. Let's say, so we just say, so for y, so for the y from 0 to, and there's a point 5, right? So 5 dy. Determine y first. Then once we determine y, then this x from this x to this x. So this x is from y to 10 minus y. Right? So x dx. Okay. So now we can integrate out, right? So this becomes a math problem. Integrate for x first, then integrate for y. Okay. Okay. So for problem 139, we want to find, we need to calculate expected number of people in the car who are hospitalized. So given that, so this means like we want to find conditional expected value, right? Conditional expectation. Okay. So we say the number of people who are injured or hospitalized. So let's check. Okay, the problem. So here a driver and a passenger. So in the car we have only 2 people. Okay. So let's say, so the number to hospitalized can be only like 0 or 1 or 2, right? Only can be this case. Okay. Okay. So what is the probability? Let's say each of them independently has a probability of 0.3 of being hospitalized. So we can find both hospitalized is 0.3, 0.3, 0.3 square. So 0.009, right? And so here is 0.7 square. We can put it like 0.7 square, 0.3 square. Yeah. So this is both of them not injured. And one injured is thus, so like a 2. So we just put this numbers. So here we find this equal 42. Right? Just make this totally is 1. Or we can say like this guy, 1 injured, 1 not injured. Okay. Okay. So then condition is we need to check a condition. Condition is total loss is less than 1. So this is a condition. Okay. So we just check it. So total loss is less than 1. So this is total loss is 0, less than 1. Yeah. And here, total loss. What is total loss? So this total loss is uniform distributed between 0 to 1. So if only one person injured, the loss is less than 1, right? So here we just put this as x, loss as L or as x. So this less than 1 is okay, right? Let's say this loss x less than 1, okay. So in this case, maybe loss will be larger than 1. So here we just check. So if 2 persons got injured, then the total loss is, let's say this is from 0 to 1. The other one is also from 0 to 1. So both together. So the loss is just a two-dimensional distribution, and the total loss x plus y. So x plus y. So this is x plus y equal 1, right? This x plus y equal. So we can say like here total loss less than 1, and here total loss larger than 1, right? So for this case, we just check two parts. Total loss larger than 1, total loss less than 1. So we find half, right? So here the half. So for this 0.09, we put it half. Okay, so half loss is larger than 1, the half loss less than 1. So conditions, we just check total loss less than 1. Okay, so we have this. So this probability. So here is 0.7 square. Here is 0.72. So both case total loss less than 1. So but here we cannot take all, we just take half. So this equal this, right? Half part. Okay. So but this is conditional probability not totally not equal 1. So we just make this equal 1. So we just need to divide by total. So total, let's say, so here 49 and 42 and 5. So we totally just 5. This 5, 9, right? So totally is just 9. So divided by 955. Then this becomes the conditional distribution. Okay, so now we can find the expectation, right? So n equals 0 multiply this, forget. So equal 1 multiply. So probability not 42 become 42, or we just say 420 over 955. Okay, so then plus 2 multiply, so probability so become 45 over 955. Okay, so the answer is so some calculation. What is the answer? We are 0.534 like that, 0.534. Yeah. Okay. So here the key point is the conditional distribution. We should make the total probability is to be 1, right? Okay. So for this problem, it is like if we have a hurricane, and so this hurricane comes, so will cause some damage or no damage. So damage is 0.4. Like if there come this, we have damage 0.4 chance damage. And then 0.6 and no damage, right? Okay, so what do we want to find? We want to calculate the mode of the number of hurricane. So at first, what the mode meanings? So mod is in statistics, mod is the number appears most. So suppose like we have this the data like this 1, 2, 3, 3, 3, 4, 4. Then we say mod is 3, right? This 3 is mod because this it appears most of the time. So in statistics, in probability, the probability the highest is mod. Suppose that we have this x. X can be 0, 1, 2, okay, 3. And the probability is, let's say, 0.1, 0.3, 0.2, and 0.4. Then says x equal 1. 1 is mod because it is the probability to appear is the highest. Okay, so this we at the first we understand this notation. What is mod? Okay, so this means that we regard this as landing variable, number of hurricane. We want to find which number makes the probability the highest. Okay, so this is mod. Okay, so this number is it take for the home to experience damage from 2 hurricanes. So means like if we have 2 damage, so what is the n should be? So n equal 0 or cannot equal n equal 1, cannot have 2 damage, right? So n can be from 2, 3, 4, and in until infinity, right? So let's say what is the probability? So n equal 2. So n equal 2 is both 2 damage. First one damage is 0.4, right? 0.4, so 0.4 square. So what is the n equals 3? So we have 3 hurricane should have exactly 2 damage. So this means first like this means we have 3 like damage here, and or maybe here the damage. So 1 damage is that here. Okay, so could it be damage here, or the second one no damage, or could be like damage, no damage, or no damage, damage, like that, right? Okay. So let's say, so in general, those things we should realize such distribution is a negative binomial distribution. Or we can check this probability. Maybe also we can find those probability. N equals 3. What is equal n 3? So equal, there's 2 cases 2, like 2 times 4. So 1 damage. So damage happening twice. 0.42, and not damage 0.6. Okay. So and n equal k. So n equal k. So we need a little bit. So here we have the last one damage here. Then for those k p with k, we have at least we just have 1 damage, right? So here 1 damage. So from k minus 1, pick 1, and this damage is 0.4, and not damage 0.6, k minus 2, right? Then last one damage 0.4. So we we have this. So equal k minus 1 and 0.4 to 0.6 k minus 2. Okay, so now we want to find this k such that this probability is largest. Okay. Okay. So those problems, so we just let's say like we let so we just check this function. We just let k minus 1 equal x. So this constant we don't care. So this here we have this function x 0.6 x. We want to find which x make this function largest. So we can check x equals some numbers, or we can also use derivative. So let's use derivative. Okay, we let this derivative equal 0. So derivative equal 0x derivative 0.x plus x times 0.6 x times log 0.6. Let's say, so here we use this ax derivative equal ax ln log a, right? So we let this equal 0. 1 plus x log 0.6. So we let this equal 0. So we find this x equal negative 1 over ln 0.6. Okay, so we can find this, and so k. So we can find this k. And so we just find, so this is not an integer, so we just find closed integer. Okay. Okay, so this is problem from 130 to 140. Okay, so we can stop here. And thank you for watching.